Thank you. Hello, everybody. My name is Daniel Carvalho. I'm a last year PhD student at Maastricht University in the Netherlands. And today I'm very honored to present a part of my PhD project entitled here Thyroid-on-a-chip, an in vitro organoid device to test thyroid disruption. So today we know that human civilization is continuously exposed to an extensive amount of synthetic chemicals and also air pollutants. And some of these chemicals have brought profound changes in our ecosystems with major changes and impacts on wildlife and also our global climate. But also other chemicals have been causing serious health issues in the human bodies by interfering with the hormones of our endocrine systems. And these chemicals are known as endocrine disrupting chemicals, in short EDCs, and they are spread everywhere in our environment. Some good examples of EDCs are the polycyclic aromatic hydrocarbons, BAP and BKF, and these are derived from the burning of fossil fuels. And the exposure to BAP and BKF has been shown to increase the levels of infertility among men. Other very well-known example is DDT, which is a pesticide that has been banned in the US because of its carcinogenic and also endocrine disruptor potential. But what is concerning is that EDCs currently are spread even in daily products, so products that we are in contact during our daily lives. For example, the cosmetics that we use, the clothes that we wear, and even, for example, in this case, the BPA, which is also a very known EDC, bisphenol A, which was found to leak from the plastic bottles into the water that we drink, and even into baby formulas. And over the last decades, it has been shown that these EDCs affect particularly the thyroid gland. And the thyroid gland is an essential part of our endocrine system because it's responsible for regulating crucial physiological processes, including growth, metabolism, and development. And it does that by the production of the thyroid hormones T4 and T3. And what has been shown is that EDCs can cause an effect on the production of T4, and by doing that, exposure to EDCs has been shown, has been associated with an increased prevalence of, for example, hormone-related cancers, reproductive and neural disorders, obesity, and heart diseases. So currently, we are facing a big problem, and despite all the regulatory and governmental efforts to stop the spreading of EDCs, these chemicals are still continuously being released in the environment. And this is because we still don't have a proper way to identify whether a new chemical going into the market can act as an endocrine disruptor or not. And this stems from the fact that current toxicological assays, they are still based on 2D cell cultures or animal models that either do not represent the complexity of the thyroid or do it but in the wrong species. So there is urgent need to develop better in vitro thyroid assays so that we can stop the spreading of EDCs. And that's how our consortium, our European consortium called SCREEN, came on board. And here we want to develop advanced 3D in vitro methods to evaluate effects of EDCs on the thyroid gland. Our main objectives is to identify thyroid disruption and, very importantly, at relevant doses. So these are very low doses in contrast with what we normally study in this field that are higher concentrations occurring during, for example, accidents in industry or occupational exposures. So here we are talking about in the range of 1 nanomolar. Also, we want to develop a platform that is able to screen multiple EDCs at the same time. So we started by looking into what is the optimal thyroid model that we can use. And as you already heard and know, on one side, we have 2D cell cultures, and this has been extensively used on the thyroid field, but they are simplistic cell models. On the other, we have the animal models that are complex. They can recreate the complexity of the structure and functionality of the thyroid, but does that in the wrong species. So nowadays, to bridge the gap between these models, we can, of course, have organs on chip. These are engineered micro devices where we can control the environment that we offer to the cells. And now we also have this tremendous promise in the field of organoids. These are stem cell-derived 3D multicellular constructs, and they bring a lot of groundbreaking results because they are highly physiologically relevant. So they can recapitulate the complex structure and the anatomy of the thyroid, but also bring the functionality in vitro. The problem is that they still suffer from a lack of control. So it's very difficult to get a good normalization of the size, the numbers, and so they are susceptible to inter-organoid variability, patch-to-patch variation as well. And what has been recently proposed is that while organoids rapidly advances and we are getting more organoids new that are more increasing levels of complexity, there is a pressing need to combine organoids with organ-on-a-chip so that these innovative microphysiological systems can support and can control organoids. And as Matthias Luthoff said yesterday, to bring organoids as a predictable and also validated assay that we can properly analyze. So we chose, in the case of the thyroid, to go into this field of combining synergistically organoids with organ-on-a-chip, but we immediately faced with this challenge, is that integrating organoids into organs-on-a-chip can bring additional complexity. And this is mainly because traditional organs-on-a-chip are irreversibly bounded to a substrate so that we can create reliable and leak-tight sealing. But by doing so, there is no direct access to the cell chamber, and organoids need to be loaded or unloaded through very narrow microfluidic channels. And this often results in laborious, complex, and inefficient cell culture protocols. So to facilitate integration of organoids on chip, we explored the use of clamping devices. So these clamps can be used to create, instead of a permanent bonding, a reversible sealing so that we can open and close the device whenever needed. So we have now direct access to the cell chamber, and we can easily and quickly load or harvest the organoids. So following this approach, we develop a very simple device where we use a set of screws to reversible seal our system, and we combine it with embryonic stem cell-derived thyroid follicles that have been shown previously to bring the 3D structure of the thyroid follicles with expression of key thyroid genes and also T4 production. These organoids were cultured previously into a membranous carrier that would allow the transfer of the organoids in and out of the device. And this membranous carrier, we do it by our microthermoforming technique, where we start with a polymer film that is pressed against a brass mold, and with increase of temperature and pressure, we can pattern, press the film into these features, and after cooling down, we can demold the membrane, and we replicate the different patterns into this carrier. And as you can see, for example, this is quite useful if we want, for example, to create a confinement, a physical boundary for the organoids so that we can better organize them in culture. Moreover, when we integrate this membrane in our device, we can create an upper and lower compartment. The membrane can also be porous by etching, and with that we can create a multitude of different flow regimes throughout our device. So we started by testing our organoid on a chip by exposing the thyroid follicles to a known endocrine disruptor, in this case BKF, which is an air pollutant derived from the burning of fossil fuels. So we started by differentiating thyroid follicles, then we cultured them in the membranous carrier, and after 3 days in pre-maturation in culture vessels in static conditions, we assembled this membrane inside the organoids on a chip devices we applied flow, and also we exposed BKF. And after the time point, we dismounted the devices and we harvest for assessing the thyroid functionality and also transcriptomic analysis. What we found with immunohistochemistry was that the thyroid organoids inside our device were able to preserve an in vivo-like structure where we could see these luminal compartments where T4 was secreted and accumulated. More interestingly, when we compared to static controls, we saw that flow was able to increase the proportion of follicles that were accumulating T4. And this suggested that the flow could have a potential a positive influence over T4 production. Next, we analyzed the transcriptomics, and what we saw was on the graph, the blue graph, we saw the top 10 genes that were differentially expressed, and the first two were the CYP1A1 and CYP1B1, upregulated, and these genes are part of the activation of the AHR pathway, which is a known molecular initiating event after exposure to BKF. So these results indicate that organoids inside our device not only were able to detect BKF, but also to respond accordingly. Furthermore, we observed that BKF exposure downregulated the expression of key thyroid genes, for example, NIS, which is an important transmembrane protein for the uptake of iodide into the thyrocyte, but also TPO and OXO2, which are proteins important for the conversion of thyroglobulin into T4. So this data was quite promising, but still we were far from being able to screen multiple EDCs using these devices. So next, we developed what we call a microphysiological flow battery. You can see here the schematics on the right. So in this manifold, we were able to incorporate into a compact volume the reservoirs, where we have the cell culture media loaded with the different EDCs, and up to 6 organoids on a chip. And underneath we have the peristaltic pump, and everything is connected via recirculating tubing systems. What is interesting in this system is that now we, instead of having one cell chamber per device, we were able to thermoform 3 compartments, so that when we close the membrane inside the organ-on-a-chip device, we can have 3 independent cell chambers. And with that, we were able to upscale our system and screen up to 16 different EDCs. And these EDCs were chosen from 4 different classes. We have the phthalates. These are chemicals that are present in plastic products. The flame retardants, that there is still not much consensus if they can act as endocrine disruptors, and these are chemicals present in resins and construction materials. We have PCBs that are very well-known endocrine disruptors, and these are present in electronics, and we have the polycyclic aromatic hydrocarbons. In this screening, we also did an acute dosing, so high concentrations, which is often used in research, but also the daily chronic dosing, so at very low concentrations to mimic the dosing that we are all exposed during our lives. And finally, after exposing to the different EDCs, we easily open our device, we harvest the membranes, and we collected the organoids for transcriptomic and proteomic analysis. In this picture, you can see up to 2 fully assembled flow batteries, and for these experiments, we use up to 3 inside the same incubator. Next, you can see the differential expression analysis for genes that we observed, and you can immediately see that the thyroid follicles responded differently according to DC classes. So you had the polycyclic aromatic hydrocarbons having the strongest effect on the differentially expressed genes, followed by PCBs and phthalates, while the flame retardants had the lowest impact on the differentially expressed genes. Also, BAP, BKF, DAHA, and PCB126 were the ones having the strongest effects. And next, we were curious to see if any of these chemicals could have cause a dysregulation on key thyroid genes for production of T4. And what we found was that indeed there was many of these EDCs that caused upregulation or downregulation of key thyroid genes, including again NIS, TPO, and OXO, but also thyroglobulin, which is a precursor of T4, and the transcription factors PAX8 and NKX. And we also observed that BKF, BAP, and PCBs had the strongest effect in the key thyroid genes. And what was very interesting for us was that we observed that even at very low concentrations, EDCs were able to cause dysregulation of the expression of these key thyroid genes. So in conclusion, we were able to demonstrate that embryonic stem cell-derived thyroid organ-on-a-chip is a promising model, and currently we are trying to validate this system with in vivo data, and also we are trying to translate it to a human iPSC-derived model, and that our upscaled flow battery can allow the screening of multiple EDCs, and also it's compatible with mechanistic analysis, so we can do transcriptomics and proteomics data that we are still analyzing, and this is very important because we can have a better comprehensive study about the underlying mechanisms after exposure to EDCs. And also we demonstrated that even at very low doses, EDCs can cause an effect on thyroid genes. So I would like to thank all my collaborators and the funding companies for supporting this project, and also my supervisor, Professor Stefan Gieselbrecht, and also your attention. Thank you.
Thank you very much, Daniel, for the very interesting talk. There's still time for questions, sorry.
Thomas Stig-Hartmann from Bayer. Did you correlate your differentially expressed genes with T3 and T4 output?
Yeah, thank you, good question. So during our work within the consortium, we faced many challenges to quantify T4 and T3. So that was one of the main goals, also because we have collaborators that are, they want this quantitative data to bring computational modeling on board. We tried first ELISA, but it was not sensitive enough. And now we are trying to find ways to do mass spectrometry to analyze T4 in conditioned media. But that's still quite challenging and still ongoing, unfortunately. But it's very important to have that, indeed. Yeah. Thank you.
More questions? I have a short question myself. Typically, when we use polymers, we are also concerned about absorption of the chemicals into the polymers. Is that the case for EDCs?
Sorry, can you repeat?
Do you have cases of absorption of the molecules into the polymers that you're using by thermoforming?
So you are asking if we have absorption of EDCs into the tubing equipment that we use. So we try to analyze what were the levels, and we did mass spectrometry for some of the compounds to see the losses, but we were not able to get good data. But that's why we were focusing first after the exposures to see if the follicles were able to detect if the chemicals were still there, and we got good indications that they responded to the different chemicals. But we are not sure in terms of percentages what are the losses through absorption or adsorption. But it might be considerable in this case, yes.
Thank you very much. Let's thank the Pinker once again.
Thank you.